So this is the first question. It's pretty much two springs and there's a block in the middle, and it is going to be stretched to x equals x1. So this is its distance that it stretches. So this one compresses this much, and this spring extends this much. And then it is released, and then we're asked questions about it. So the first question is, in scenario 1, the block oscillates with period t. The position x of the block in scenario 1 as function of time is shown in the figure above. So on this graph, don't look at the red, just the black line, sinusoid. So this is the time, or the period, you could say, and the y-axis is the position of the block. So at x1, it is right here, right? X equals 0, right here is its equilibrium point. So then the question that C is asking is to sketch the kinetic energy of the block as a function of time. So we can base this kinetic energy off of the position one. However, it's saying this one has friction, so we have to involve friction. So what can we do? Well, how do we do this? So first, we're doing kinetic energy with friction. So kinetic energy is dependent on velocity equals 1/2 mv squared. The mass doesn't change. The velocity is the only changing aspect. So that is what's going to change the graph. So initially, when it's at equilibrium, when nothing's happening to it, its kinetic energy is what? Well, it's 0. Nothing's happening. There's no velocity. So that means 1/2 mv squared. The m, there is an m, but the v is 0, so this all equals to 0. The kinetic energy equals 0 when it's at equilibrium. However, once it is moved to x1 and it is released, then it has a kinetic energy. However, it's not increasing linearly, right? It's not like that, because it's gaining speed, it's accelerating, so it's gaining velocity each second. So that means it has to increase like curved. So it curves up, right, all the way, this is kinetic energy, right, to its highest velocity. So when is it at its highest velocity? Well, that is when it is at the equilibrium point. So right when the position of the block is at 0, which is seen, which is seen here, when it's at 0, it's at its max velocity. So when it's at its max velocity, its kinetic energy is the greatest. So that would be here. This is the highest kinetic energy. Then once it goes past this point and it keeps going this way, and while friction's acting on it, it will lose kinetic energy. So once it'll reach its back to x1, so let's say it travels all the way back and then it goes a little less than x1 because friction, then it's at its half period, right, the kinetic energy will be 0 because there's no velocity, it's at a standstill, right? So here's the boom, and then this one. So it's there and it gets released, and once it reaches this x1 here, then its velocity is 0, it stops, so kinetic energy is 0, so right here. Then it'll go back up again like the same thing. However, there's friction, so it won't reach the same kinetic energy. Its velocity will be lower, and it just continues that pattern all the way through. So that is how to do the question C. So in the next question, D, it is pretty much replaced, the same system is replaced with a new block of larger mass. So it has a greater m, and it's asking, describe how one feature of the graph, the one we just kind of drew, as a function of t. In scenario 3, this one would differ from the graph we just drew. So, well, if it has a higher mass, then that means its normal force, which is its friction, which equals mu times normal force. Its normal force would be increased, so that means its friction would be increased as well, resulting in more of a drastic decrease in kinetic energy. So this one, it would decrease greater for every period because there is an increased normal force. So normal force is mg in this scenario. So if m is increased to a larger mass, it would be an increased normal force, so more friction is happening on this on the block. So there's one possible scenario you could do. Then also its kinetic energy will start at a higher point on the graph because it has a greater mass. Kinetic energy, right, we just did, equals 1/2 mv squared. So its mass would be increased, right? So that would mean there's more kinetic energy to start out with. So instead of starting out, for example, from this point, it could increase even higher to like up here potentially. So that is another possible explanation. And then finally, another one you could do is it's a longer period. So the angular velocity is equal to root k over m. So with a greater m, it would result in a lower w. So and w equals 2 pi times frequency. Frequency is 1 over a period. So with all of this, with a greater mass, it would result in it would take a longer time for the thing to actually oscillate back and forth. So there would be a longer period, pretty much. But I recommend you do the first one because it just makes it's the easiest one to do, I think, because think about it, friction, if there's greater friction, then its decrease in kinetic energy is more drastic than if there were less friction because of the normal force. So that is how to do D. Okay, the next question is this system here. There's a pivot, a stopper, a block, and a box, and it is at a specific height, and then it is going to be released once the height equals 0, and it will be then continue to travel. And friction is negligible, so we don't have to worry about that. And the one that's focused on the test is B, not A. So describe how the data collected in part A could be graphed and how the graph would be analyzed to determine the value of G. So what is the energy that we have to set up to equate what this whole system is? Well, it's potential energy equals kinetic energy. And potential energy is mgh, and kinetic energy is 1/2 mv squared. So what we could do if we are trying to solve for G, and we have to set up how that could be graphed, well, in this graph, we have to set up y equals mx plus b. So how can we do this? Well, using this mgh equals 1/2 mv squared, we can set up a y equals mx plus b equation. So if we are solving for G, our G is going to be our slope, which is our m. So what can we do? Well, we can cancel out whatever we can do to simplify this. So what can we cancel? Well, the m's. So the m's are gone, and we're left with gh equals 1/2 v squared. So then let's look at our equation, y equals mx plus b. Well, if G is our m, right, then what is our x? Well, h, because mx. And then what is our y? Well, it's on the other side of the equation. So y equals mx. And then if you ask, well, what's the b? Well, there is no b. The b is 0. The y-intercept of this graph is 0. It starts at 0. So that means our b is 0. So using this, we can set up a graph that looks like this. So our x on the x-axis is our height. So this is our x-axis. And on the y-axis is v squared over 2, which is right here. And then if you graph these two and graph data points on them, you will get a line of best fit that is equal to a slope of 9.81 around. So that is one possible procedure of how to find the slope or determine the value of G using this equation of y equals mx plus b. Okay, the next question or the next part of the question is it includes friction. So now that there's a friction coefficient involved, we have to account for that. So the question is pretty much asking indicate two quantities, either measure quantities from table 1 or additional calculate quantities that could be graphed. So again, we're dealing with a graph, so we have to come up with a line, right? Y equals mx plus b. A straight line, right, indicator, that could be used to determine the value of mu. So again, if we're trying to determine the value of mu, our mu is going to be our slope, which is also m. So m equals mu. This is slope, not mass. Okay, so, well, what is this setup? So if we're involving mu now, friction, we can do kinetic energy equals potential energy, and all of this is going to equal the frictional energy lost, right? So we can do friction energy. That'll be our symbol for that. And what is frictional energy? Well, it's mu mgd. So, in order to cancel out the most things, instead of using 1/2 mv squared, we can use mgh. So we see we have m and g that are in common, and we can cancel those out. So setting these two equations up, we'll do potential energy and frictional energy lost. It'll be mgh equals mu mgd. So this system set up, we can cancel out the m, and we can cancel out the g. Now we are left with h equals mu times d. So again, if our slope is m and our m is mu, this is our slope. And so what is x? It is d. So, right, because mx. And what is h? This is y. So now we have our equation. And again, there is no b here. The b equals 0. There is, nothing that can be the b. The b is 0. It starts, its y-intercept is here. It starts at 0. So what does our equation actually look like? Well, let's go down here. Y is h equals mu d, right? So again, our slope we'll be solving for, that is our mu, and our graph looks like this. Our h as the y, and our d, which is our x max, as the x-axis. So just answering the question, vertical axis is h, and horizontal axis is dx max. Okay, the next part of the question is asking, it's pretty much really simple. It's just graph the data points and then draw a line of best fit, which is, I hope you know how to do that. If you're given the data points right here, this is x, this is y, right? Sorry, this is y, this is x. So you graph these on the horizontal axis here and the vertical axis here. Once you graph those, you should come up with a line of best fit. Right? You graph the data points, do the closest one, and then find the slope of that. So find 2 points on the line, delta y over delta x, that is your slope. So for the one I calculated, my theoretical slope is the friction coefficient equals 0.5. That's the one I found here. But again, this is different for everyone because no one's line of best fit is going to be the exact same. So, well, the actual one, by the way, is 0.38 if you go data point by data point. So, but if it's asking to graph for two quantities that you plot, you use the line of best fit to solve for that one. So, yeah, just graphing and line of best fit, you should be able to know how to do that. And then, yeah, use the best fit line that you drew right here to calculate the experimental value of mu. So, again, delta y over delta x, and you can solve for your slope. Okay, our next one is this system here. So block A and block B, blah, 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 blah. So it's compressed, and then it is released, and it goes through a non-frictional surface, then it goes through a frictional surface for a certain distance, and then after that, it continues, and it hits this block B in a collision. So, our first question. Our first question is derive an expression for the speed v of block A at time t1. Well, what is t1? At time t equals t1, block A is at x equals x1. So x equals x1 is right here, right before the frictional distance that it travels. So Block A moves with speed v, and the spring is at its equilibrium position. So derive an expression for the speed, right? What we did. So what can we do? Well, we can do our potential energy of spring is equal to our kinetic energy. And what is our potential energy? It's 1/2 k, and then it is xc squared, because their indication for the distance that it is compressed is xc. So 1/2 k xc squared equals 1/2 mv squared. So using this, if we're just deriving an expression for the speed of v, well, we just have to isolate v, which is quite simple. So we can cancel out these 1/2s, right? So we're left with kxc squared equals mv squared, and then divide by m. So each side divide by m. So kxc squared over m equals v squared. What's the final step? Square root both sides. So your v comes out to root kxc squared over m. And that is an acceptable answer for deriving an expression for the speed v of block A at time t1. Okay, the next one asks derive an expression for the speed v/ab of the two-block system immediately after the collision at time t3. Well, what is time t3? At time t3, block A is at x equals x3, and block A collides with and sticks to block B. So x equals x3. Where is that? X equals x3, so right here. So it is colliding with this block B and connecting to it and going at a velocity. And the question asks, what is the speed v/ab of the two-block system? So there are two things we have to do here. So first, we have to find the velocity initial of block A. So if you think it's this, it's not. This is before it undergoes the frictional surface. So if we have to find the velocity after it undergoes that frictional surface, so it's going, right, it has a velocity, then its velocity slows down, and then it remains the same. So we have to find the velocity at this moment, so to set up our momentum, conservation of momentum equation. So what can we do? Well, now we have friction involved. So let's do, it's 1/2 k xc squared equals 1/2, this is our kinetic energy, 1/2 mv squared, and then it's one more thing that we're missing, plus our mu mgd. So this is all the energy setup in it. So it undergoes the kinetic energy and its loss to frictional energy, and it is all powered by this potential energy in the spring. So first we should isolate that. What we're solving for is this v right here. So let's use our algebra to isolate it. So first thing we can do is we can subtract this part on each side, so we can get 1/2 k xc squared minus mu mgd equals 1/2 mv squared. Then we can multiply each side by 2, so we get 2 times 1/2 k xc squared minus mu mgd equals mv squared, right? And then we can divide both sides by m. So also we can distribute this 2 to make it easier. So 2 times 1/2 is 1, so k xc squared minus 2 mu mgd all over m equals v squared. Last step, square root the v. So our v initial equals, after it undergoes friction, equals root k xc squared minus 2 mu mgd all over m. So that is our v initial after coming out of that frictional surface right here. So at x2, our v initial is this equation right here, expression, whatever. Now, it is asking what is the velocity after, right immediately after it collides with this block right here. So if block A is mass m, block B is mass 3m, we can set up our conservation of momentum equation. So m1 v1 plus m2 v2 equals m1 plus m2 times vf. So let's plug in these numbers that we have. So m1, so we can just do m times v1, which is initial, so times root, which we just solved for, root kx c squared minus 2 mu mgd over m, right, plus, well, block B has velocity 0, so this, if this is 0, then the whole thing is 0, so plus 0, so this really doesn't matter, equals, so m1 plus m2, well, m1 is of mass m and m2 is of mass 3m, so if you add those, that just is 4m times vf. So our question is asking what is VA, or what is our VF. So let's just isolate it. So if this is like that, we divide this by 4m. So we get VF equals m times root k x c squared minus 2 mu m g d over m. And this entire thing is over 4m. And what we can do, we can simplify it even more to where we can cancel this and this out, and we can get our final as VF equals root kx c squared minus 2 mu mg d over m over 4. Boom. And that is how to algebraically isolate for VF or VAB. Okay, the next part is on the following axis, sketch a graph of kinetic energy K of block A as a function of time, from time 0 to time t3. So our first interval is from 0 to t1, which is from x0 to x1. So it has potential energy from the spring of 1/2 k x squared, and then that is converted as it travels through xc, or as it travels through this distance to kinetic energy. And its velocity continuously increases, so it's not going to be a straight line increase. Instead, it looks like this. It starts at kinetic energy of 0, and it slowly, or not slowly, but it gradually increases, and it's not direct, it's not constant. Its velocity continues to increase. So that is from 0 to t1. Then from t1 to t2, it is this. It is traveling through this frictional distance. So what happens? Well, its kinetic energy, its velocity is going to decrease. So that means its kinetic energy will decrease as well. However, again, it is not linear. It is not at a constant rate. Instead, it's curved, because its velocity slows down. So as it's slowing down, it is there for a longer period of time. So it's not, its velocity decreases not at its constant rate, like I was saying. And then from T2 to T3, which is from X2 to X3. Well, there's no friction, so nothing's happening, so it will continue at that constant. However, whatever it left out on here, its kinetic energy will continue through all the way till it hits here. So that's kind of what we did in the past question. Like I was saying, we have to solve for this velocity right after it comes out of this frictional surface, because it'll remain the same all the way up until it hits this block, right? Okay, the next question for this problem, it's basically after the block A hits block B and they're connected, they swing on a pendulum, and it's asking what the difference in frequency would be for a pendulum, for the two pendulums, one with length L and one with length 2 times that, with 2L. So basically, frequency depends for a pendulum depends on its length. So a longer length, it would have a longer period, and frequency is inversely proportional to its period. So if it has a longer period, then it has a lower frequency. So because frequency is how many times it swings back and forth. So our answer would be the frequency of the longer length pendulum is less than the frequency of the shorter length pendulum. And we can do this with a physical demonstration, which I will show. All right, so using this lightning charger, we can demonstrate this. So let's say our the first pendulum with length L this is length L, right? So if we set this, right, and we let it swing, it's about that speed. Not too fast, not too slow, but, you know, that's, so frequency is how many times it does that in, like, a period, for example. And then if we increase this by times 2, this should be about good enough, and we do that same thing, it goes much slower. See, it goes like that, compared to the one where the length is much shorter. It's much faster. It oscillates more times. So if you just kind of think about this, you can get to the right conclusion when answering that question.